Hello and welcome to this tutorial on non-negative matrix factorization, also known as non-negative matrix approximation. Table of contents. First, we're going to describe what a non-negative matrix factorization is. We're going to discuss some techniques and methods of approximation. Then, we're going to give an illustrative example of why non-negativity is relevant. And finally, we're going to give the conclusion. So what is non-negative factorization? Non-negative matrix factorization is a group of algorithms in linear algebra where a non-negative matrix is factored into two smaller matrices in such a way that the two resulting matrices are also non-negative. Unfortunately, the problem of factoring the matrices exactly is not solvable in general. This is not solvable in general. The current method of getting around this is to approximate the matrix by two non-negative matrices. That is, the problem is, given C a non-negative matrix, find A and B such that C is equal to A and B, where A, B, and C are all negative. This is not solvable, so we're going to solve the new problem, which is find D and E such that C is approximately equal to D and E, where D and E are non-negative matrices. So how do we define approximation? Well, we can't talk about approximation unless we have a metric which defines the distance between two matrices. So we're going to have to define a metric, actually not necessarily a metric, since a metric requires symmetry. We're going to have formulas for A and B that are not necessarily symmetric. We'll see in the next slide. So here are some examples of metrics, or you could call them pseudometrics, on the set of matrices. These metrics, in quotes, are sometimes also called cost functions. Here are two which were studied by Daniel Lee and Sebastian Sung. Distance between A and B, the first one is the Euclidean norm, which is the sum over all of the components in the matrix squared. The second is the divergence of A from B, which you can read in the formula there. Note that both of these formulas are bounded below by 0. Second formula is not actually a metric, that's why it's not symmetric. We're now ready to state problems in non-negative matrix factorization. The first problem is to minimize the Euclidean norm with respect to H and W. So that is, we range over all H and W, which are non-negative matrices, and try to minimize that Euclidean distance. The second problem is to minimize the divergence of V from WH with respect to all W and H greater than or equal to 0. Here are some of Lee and Sung's work on solving these problems. Theorem 1 is that the Euclidean distance is non-increasing under the following update rules. First update rule is that we take H and we multiply it by the transpose of W and times V, then we divide it by the transpose of W times WH. So we start off with some initial HW and we update them according to the rules you can see there. Note that if we update H and W, we're multiplying them, and so if we have a fixed point, that is if HV is equal to WH, then we're just multiplying it by the identity. So Lee and Sung also proved the convergence of these update rules. Note that this yields a local optimum of problem 1. So looking at getting a local minimum. We have no hope of finding a global optimum in general. Why is this true? We have no hope because although the distance between V and WH norm squared is convex in W and H separately, it's not convex in both variables jointly, and from what we know about basic properties of convex functions, we see that we have no hope of finding a global minimum in general. Some further results by Lee and Sung. They found an updating algorithm for W and H for which the divergence from V to WH is non-increasing, so the analogous result for the divergence. They also prove that the divergence converges as W and H are updated, hence we can always find local minima for problems 1 and 2. Some cons of Lee and Sung's method are, unfortunately, this iteration scheme may require thousands of iterations before we get closeness or convergence, or we get that the distance between the matrices are small, or convergence. So also we have to choose initial points, and depending on those points, convergence may be slow, and the minimum that we reach might be large in relation to the true global minimum that we would like to have. So now what? Now we are well equipped to apply non-negative matrix factorization methods. We can approximate and find hopefully decent optimum. Why do we care about non-negativity? That's the main question. The reason that non-negativity is important is that in many cases the values of the matrix represent the existence of some object, such as the number of times a word appears in a document. That's value in the matrix. So you're going to see that if we allow for negative numbers, it would make the results difficult to interpret. So we have a news article example. So consider a large matrix where each row represents a news article and the columns represent words. So the ij entry is the number of times the word j appears in article I. So we want to extract features from these news articles. So we want to see what the main ideas in the articles are. So just note there might be multiple features in one article, and some features there might be a feature that's in many articles. It doesn't matter. We allow for this flexibility. So how do we extract the features? A way of doing this is we factor the matrix into two smaller matrices, the features matrix and the weights matrix. And these are going to be non-negative matrices, and they're going to be feature matrix is going to have rows as features and columns as words, and the weights matrix is going to have rows as articles and features as columns. So these features, these are going to be basically the themes that we're trying to understand that are in the articles. So we don't have a description of what these themes are. We're going to be looking at the features matrix and trying to understand what the themes are in there, and if in the articles. And if the matrix entries are non-negative, then it's going to be really difficult to understand what the main ideas in the article are. For example, if I have an article and the word beer is in it 20 times and beach is in it 10 times, then I know it's about drunk people on a beach, people drinking on a beach. But that's a lot easier to understand than if the article, if it says the theme, if it says that the theme is that cat is in there negative 10 times and duck is in there 7 times. I have no idea. You have no idea what that means. The weights matrix basically transforms the features matrix into the initial articles matrix. So A is equal to FW. So we understand the weights matrix is something that's taking the features matrix and taking some linear combination of the features matrix and giving you back the articles. So it's just that an article is some combination of features and whatever weights that it is, and that's what the weights matrix represents. That also needs to be non-negative or it doesn't make any sense. Other applications are to computer vision, clustering, chemometrics, and recommender systems. Currently, there's a lot of research being done in matrix factorization. So in conclusion, we have defined non-negative matrix factorization, shown exact methods of finding local minimalist solutions, not global, for approximating the non-negative matrix. It's not solvable in general. Recall, we've given a concrete example in which is a value to factor a matrix into two non-negative matrices, and we have shown why it's clear that these matrices must be non-negative in order to have any chance of understanding what's going on, and this is what motivates the reasons behind requiring the non-negativity in the matrices to begin with. So that's non-negative matrix factorization, and thank you for watching.